PhD, the radiation safety officer here. He left us, unfortunately, and went to RIT and is now also working at a company in Buffalo. So taken from his website, Dr. Andrew Karam has an extensive experience in radiological and nuclear safety, especially in the workplace, the environment, and in the military. He served as a reactor prototype training plant staff instructor on an attack nuclear submarine for the US Navy's nuclear power program for 8 years, and in fact wrote a book which I sort of read, but my husband loved, he did read, which was called Rig Ship for Ultra Quiet. He's an internationally recognized authority and has served on the Health Physics Society's board of directors, the National Academy of Sciences subcommittee on the effects of battlefield use of depleted uranium, and for the purposes of today is also on one of the NCRP committees. So, no further ado.
Okay, thanks. Hey, and actually the international recognition means that you know who I am too. So, but anyhow, well, and first I really do appreciate your asking me to come here. And so you're one of the few people here who I think that I really got along with well, so I appreciate the fact that you remembered me. And so, well, maybe a couple others too. But anyhow, what I wanted to talk about is some of the work that the NCRP has been doing, or the National Council on Radiation Protection and Measurements, in the area of radiological terrorism over the last couple of years. And I guess, first of all, is it safe to assume that most of you kind of know what the NCRP is or what they do? Or should I give a little bit of background on that? Okay, I see enough heads nodding. Yeah, the NCRP was founded, I think, in the late 1920s, and its purpose is to advise the U.S. government and radioactive materials users about, or to make recommendations about how to safely use radiation and radioactivity. A lot of their reports are medical in nature. For example, they've got one that looks at the transfer of radiopharmaceuticals across the placenta and what the dose is to the baby. They also have stuff on X-ray rooms, some that deal or that are relevant to radiation oncology. Outside the medical field, they've got reports basically in just about every area. Recently, they've had reports, for example, on radiation dose rate from space activities, whether it's near Earth orbit or for extended visits to the moon or to Mars. They've also done a lot of stuff on linear accelerators, industrial use of radiation in the mineral industries, and so forth. And actually it turned out in October of 2001, they released report number 138, which dealt with radiological terrorism and trying to manage the aftermath of a radiological terrorist attack. The timing of that was, I guess you could say, fortuitous. The report had been in the works for a couple of years, and it just happened to be published the month after 9/11. So since then, there's obviously been increased interest in the possibility of radiological terrorism, what the effects might be to people as well as to our society, and a little bit about the environmental impact, but not quite as much as the political or the health economic impact. And so what I'm going to talk about, I'm on two NCRP committees that are dealing with very different aspects of response to a radiological or nuclear incident. The first committee, and actually I guess I can go on to the next slide here. And I guess that covers up to here. The first committee, Science Committee 4-1, and I'm kind of in your way, aren't I? I'm sorry. But yeah, Science Committee 4-1 is writing a report that's meant to replace report number 65, which of course explains everything. But basically what we're doing is coming up with a replacement for a report on how to manage contaminated people. Report number 65 was released about 25 years ago, and it was specifically titled Management of People Accidentally Contaminated with Radionuclides. And we realize that accidental contamination is the least of our concerns now. So we're addressing things like the polonium poisoning of Litvinenko, as well as radiological attack, an accident with a nuclear power plant or an attack on a nuclear power plant, but basically just looking at how you manage people from the time that you find out that they're contaminated until the time that you make the decision as to whether or not they should be admitted to the hospital. So that's, and I'll be spending a lot more time talking about both of these in a couple minutes. This is just kind of an overview. The 4-2 committee basically picks up specific aspects of, or basically picks up where the NCRP 4-1 committee leaves off in some very specific areas. And specifically, in that committee, we're looking at the rapid assessment and decontamination of large numbers of people who have been contaminated internally with radionuclides. So, for example, with the 4-2 committee, we wouldn't be interested in an accident in a laboratory where 1 or 2 people are contaminated. What we're interested in is a radiological attack where maybe thousands to hundreds of thousands or millions of people might be contaminated. And specifically, we're also looking at the effects of internal contamination. So basically, if you can hose them down and dispense with the problem, then the 4-2 committee doesn't really come into play. It's only when those people have inhaled or ingested a lot of radionuclides, or for that matter, radionuclide injection, which from the standpoint of the 4-2 committee is anything that directly introduces the isotopes into the blood. So not just like, I guess, pushing syringes full of radionuclides, but people hit with shrapnel, or people with a lot of cuts or abrasions where the radioactivity gets directly into the bloodstream. Things like that are with the 4-2 committee. And one of the things that means, and I think that gets to the next slide, is that especially with the 4-2 committee, there's a big difference between how you can assess alpha and beta internal radioactivity versus gamma emitters. And I'll talk a little bit about some of that stuff first. But I've got all sorts of other stuff specifically for each committee. But one of the things, for example, is that both committees acknowledge that gamma-emitting isotopes are easy. Because if somebody inhales it, ingests it, shoots up with it, or whatever, you can see it fairly easily because the gammas will penetrate the body. And so from that standpoint, with the exception of low-energy gammas like americium-241 or I-125, with those you can have a significant amount of attenuation, even just through the chest wall. With the exception of those, pretty much, well, I hate to say it this way, but pretty much any idiot with a sodium iodide detector can figure out how much uptake there was. Unfortunately, if you really want to hurt a lot of people with radioactivity, you're probably going to do it with alpha emitters. And those are almost impossible to detect, well, with the exception maybe of americium-241 or radium-226. Those are just really, really difficult to detect externally. There are, I mean, if you've got something like radium or americium, you might be able to pick up some counts in a whole body counter or with a chest scan. But otherwise, you're basically looking until something processes through the body and shows up in the urine or in the feces, or you start taking blood samples or try to collect sputum or something like that. But basically with alpha beta emitters, you've got to get inside the body or get something as it's leaving the body in order to try to figure out how much of an uptake there was. The only alternative to that is doing something like nasal wipes or oral wipes, but those have problems also. If somebody's got a runny nose, they may pass the radioactivity, or a nasal wipe just may not show very much. Or if they spend a long time outside, then, or if there's a long time, I should say, between inhalation and actually doing the nasal wipes, you may not get anything on the swab either. So, but in the short term, within maybe several hours of an ingestion or inhalation, nasal or oral wipes is probably about the best bet that you have. I guess the best way to put it is something like that can show you that a person has had an uptake, but it cannot tell you that a person has not had an uptake unless you catch them immediately after the possible uptake. And even then, it may not be all that revealing. So again, gamma emitters are really fairly simple, but alpha and beta emitters are just really a pain in the neck. Probably about the best that you could hope for rapid assessment of a beta or alpha or beta emitter, barring the nasal swabs or oral swabs, is to hope to have something that's in very soluble form so that it gets into the bloodstream or into the urine or into the feces fairly quickly. Oh, and I guess one other thing too, if you look at the amount of radioactivity it takes to cause certain effects, you find out fairly quickly that about the only way to hurt a large number of people is with the, well, I guess from the terrorist standpoint, preferably the covert dispersal or dissemination of airborne alpha activity. And I'll talk a little bit more about that in just a minute here. Okay, Peter Zimmerman used to be the science advisor for the Senate Foreign Relations Committee under the Clinton administration, and then of course 6 years ago had to find another job. But he's done a lot of work in this area. One of the things that he was trying to do was just to estimate, roughly speaking, how many fatalities you might see from a radiological attack. And the only data point that we really have from this is an incident in Goiânia, Brazil in the late 1980s where an oncology source was, I think it had about 1,400 curies of cesium-137. It was now salvaged inappropriately, opened up even more inappropriately, and I think with about 10% of the activity that escaped, I believe it was 5 or 6 people got a fatal dose of radiation from that. So using that data point and a fair amount of arm waving, Zimmerman figured that in a malicious type attack that we might see as many as 100 people die per curie of gamma emitting activity that was distributed around. And given the higher quality factor or biological effectiveness of alphas, he felt that up to 2,000 deaths per curie was reasonable for maliciously distributed alpha activity. On the one extreme, you could have somebody with maybe a couple curies of americium-241 in powdered form that you just dump on the street in Times Square on New Year's Eve and let the wind, traffic, the foot traffic or whatever suspend that, and people inhaling it. That way he figured maybe 1,000 people per curie would get a fatal dose of radiation. If people actually how maliciously distributed or actively distributed by blowing it into, say, the ventilation system of a large building or sports arena, he felt that you could have up to 2,000 people, maybe even more per curie. And I guess the ultimate distribution would be if you just put it in an asthma inhaler and sprayed it into everybody's lungs, in which case you could have hundreds of thousands of deaths per curie of americium. And so this is what we're trying to protect against. Well, and I guess I'll just leave it at that right now. Oh, and the last thing, unfortunately, it's really easy to find reasonably high activity sources. And so, as just two examples, well logging sources that are fairly widely used in the petroleum and mining industries can have up to 10 or 12 curies of americium-241, and you don't necessarily need a security clearance in order to buy one of those. And you don't really necessarily need all that much in the way of equipment or expertise to steal one. There were several that went missing in Nigeria within the last couple of years, as well as some in Venezuela and Ecuador, and there are literally probably on the order of tens of thousands of these things around the world. Not to mention, if I were going to be doing it, I would just apply for a radioactive materials license and buy one legally rather than try to steal one. But anyhow, that's as far as the alpha emitters go. Well, I've done a little bit of talking to people with the FBI to try to explain some of these things, and I think they're starting to take it a little more seriously. As far as the gamma emitters go, that's in some senses even easier. I got a call from some people in the Philippines a couple of years ago, and a physician there who wanted to open an oncology clinic had just bought a used medical therapy source, and the Philippine government found out about it a year or so later and were wondering why the U.S. would allow shipping a high activity source to anybody with a word processor who could type up a convincing looking document. And the answer is that, and this may have changed in the last couple of years, but as of just a few years ago, all that I needed to ship a source to somebody was a copy of their license. And I could get that from them, not from their regulators, which meant that if I wanted to buy a high activity source, I could go to a place like Cambodia, the Philippines, or any other country that has a very weak radiation safety infrastructure, basically type up an official looking certificate, and then just basically troll the medical list servers until a hospital announces it's got a therapy source free to a good home, at which point you pay for the shipping and a month later you get your source. So, you know, we know that there are high activity sources available with enough radioactivity to cause a lot of problems. I have to assume that anything that I can think of, a terrorist group could think of also, because the one thing that they have shown is that they can do their homework fairly well. And I also know that, and if any of you doubt this, go to the blood bank in this facility and put an ion chamber on the side of it, or to Jackie's irradiator. And you will also find out that it's not that difficult to shield a high activity source so that it's virtually undetectable. We have to assume that other people know this as well, and that being the case, we have to assume that they have the ability to get high activity sources and to bring them into this country or to obtain them in this country, then to go ahead and use them. So that being the case, and this is kind of a long preamble, but that explains some of the urgency at the NCRP for trying to get these reports out, and also I should say some of the urgency with Homeland Security, CDC, and the other agencies who are funding these reports. And then one other thing, and after this I think we get into the actual committee work, there were a flurry of editorials within the last couple of months, I think most of them authored by Peter Zimmerman and others, about covert radiological attacks, or what Zimmerman calls a smoky bomb. Basically, it kind of goes back to what my dad used to tell me. There's no limit to what you can accomplish if you don't care who gets the credit for it. If you set off a dirty bomb, let everybody know what's happened, people show up with radiation detectors, they find out that there's a problem, chances are that few, if any, people are going to die of radiation sickness. On the other hand, if you take the radioactive material and kind of gently waft it into the atmosphere or blow it into a building or something like that and don't announce the attack, it may be weeks or longer before we figure out that one's occurred. I mean, if you think about it, say right here in Rochester, say somebody decided to spread some contamination around, downtown wouldn't be good because nobody goes there, but maybe at one of the shopping centers or something, then the first that somebody's probably going to find out about it is maybe when Radiation Safety here is doing a routine survey, they find contamination, and if they decide to chase it down, they realize that it's all over the place, not just in one particular lab. Or somebody goes into the Gannett plant and maybe sets off the detectors going into the plant. But basically, you're counting on an accidental detection to find a covert attack. And depending on where you're at, again, it may be weeks or longer before something like that's detected. Especially if you're blowing alpha emitters into the ventilation system of a large building, the first indication that there's been an attack might be weeks later when people start going to their doctor with respiratory problems. And the last I checked, pulmonary fibrosis and pneumonia were not CDC reportable diseases, which means that you could end up, say, with everybody at Madison Square Garden exposed to a high level of internal alpha activity, all going to different doctors, maybe all being admitted to different hospitals, and nobody to put the pieces together because this would happen, again, weeks or even months later. So that's one of the biggest concerns we have about the Smokey bomb, is that if Al-Qaeda or one of those who they're inspiring decides that they don't care about getting credit for the attack, all they want is a body count, this is probably more likely what we're going to see. So on the bright side, polonium doesn't seem to be really good for this sort of thing because it's so expensive. Although I would imagine a lot of disgruntled ex-husbands got some ideas from that whole saga. So, or at least that's what I got a call from a guy at USA Today, and he asked if I thought I gave any good ideas to Al-Qaeda, and I said no, but maybe to some disgruntled spouses, and he said I won't print that. But anyhow, so getting on to the specific committee reports. And I haven't considered that, by the way, for my ex-spouse. So anyhow, as far as the 4-1 committee goes, like I said, it's going to report or replace report number 65, which was published some time ago. And to be honest with you, the fact that the report that it's replacing was published so long ago has made us really careful, and it's delayed this project quite a bit because we're expecting our report to last for the same length of time. We know that it's going to be used all over the world. We also know that it's going to probably be one of NCRP's best sellers. We just want to make sure that it's something that really will still be useful a couple decades from now, as well as being relevant today and at that time. So we cover literally everything from a single person who ejects a couple microliters on their forearm or on their hand, all the way up through the aftermath of a radiological or nuclear attack, and pretty much everything in between. In fact, one of the bigger sections of this is the settings in which contamination may occur, where we just describe for each of about a dozen or so different settings the nature of the contamination. We go through the properties of the types of isotopes most likely found in those settings, and then explain what the radiological and the non-radiological concerns will be. You know, as just one example, we don't want a non-health physicist, or I'm sorry, we don't want a health physicist to go rushing into a steel mill to try to recover a ruptured cesium source and forgetting about the fact that they could be incinerated by the molten steel that's around there. You know, so we really do want to try to cover all the bases in the settings chapter. We've got just really a hugely expanded section, I guess I said vastly here, really big section on the biokinetics of different radionuclides, kind of a synopsis of the important stuff that we know about them. That includes really brand new biokinetics on a lot of these things. This section alone takes up about 200 pages of our draft report, but the guy who's doing it is the one who does all the biokinetic reports for the ICRP as well as a lot for the NCRP and others. He's just top notch. There will be some new science that's published in this part of the report. I'm also in awe of the guy who did that because he did it all himself. It's got an up-to-date, at least up to the time that we publish it, assessment of different decorporation drugs and techniques. One of the things that we're really discussing right now is how to deal with stuff that is in clinical trials as of the time the report goes to press, because we know that a lot of stuff never makes it through clinical trials. And so we're still grappling with that one. Right now we're erring on the side of completeness, but after the council gets through with it and just all the reviews and everything, we may take out some of that information. And then our committee members include a couple health physicists, a couple physicians, and for those of you who don't know, REACTS is the Radiation Emergency Action Center and Training Site. Basically, anytime there's a radiological incident anywhere in the world, they're they're usually one of the first people called, and they typically send people to respond. So these people, and Al Wiley is a physician who's the director of REACTS, he knows more about radiological emergencies than just about anybody else in the world. So having these people on the committee really makes sure that we're addressing the needs of the physicians and the emergency department staff, as well as emergency responders or health physicists or whatever else. And that was one of the problems with the report number 65. It was written primarily by health physicists and primarily for health physicists. And so this one, we really are making an effort to make it applicable, or parts of it applicable, to emergency responders and medical personnel, as well as the health physicists. That's one of the reasons why the report has blossomed from about maybe 180 pages or 200 pages to what's probably going to be a 400 or 500 page report. But I guess if you are in the habit of reading these things at night, don't lay on your back while you're reading it. You know, lie on your side or something. So as far as the new things in the report, and we still don't have a number for this one yet, which is why I still keep on saying the 4-1 report. But one thing that's new is the settings chapter, which I mentioned before. Another thing that's new, the 65 report had yellow pages that contained like a quick reference guide for health physicists. We've expanded that. I think we have 4 or 5 parts to the quick reference guide now, color-coded, 1 part for medical responders, 1 part for emergency responders, 1 part for HPs, and then just a general reference thing with thumb rules and organization guides and things like that. And this is really what we're expecting most people will turn to first, you know, to their appropriate part of it. Al Wiley's comment is that he keeps on his bedside the 65 report because that's got all the stuff that he needs in an emergency. We're hoping that this will serve the same purpose for incident commanders or for health physicists or emergency room physicians or, you know, whoever else might be called on to respond very quickly. We've also got a section on roles and responsibilities for various organizations. That way the public health director can look at it and they can say, oh, okay, this is what I'm supposed to be doing, or this is what my people are supposed to be doing during this part of the response. And the same with the incident commander or the emergency department director or whoever. This will help everybody, or yeah, this part will help everybody to know what their role should be. And then also some flow charts, and I'll show those later. And clinical decision level, which I'm going to devote a couple slides to, but basically this is designed by our physicians specifically as something to aid physicians in trying to assess radiological, or I guess we've been calling it radiological triage. So, and I will get back to the CDLs because that's one of the things that I think we're really the happiest with. So, but as far as a quick reference guide, actually I think I've pretty much covered all of this already. But again, our aim is that this will be the place where you can turn to the appropriate colored quick reference guide so that when something first comes down, as soon as I guess you can get your eyes cleared up and get a cup of coffee down or whatever, this is where you would go to find the immediate stuff that you need to know. As far as the roles and responsibility, again, I already covered a lot of this. And I do have a chart further back showing where these different areas are, but these are the groups that we address for each one of the area. Again, just telling what should law enforcement, emergency response, public health, incident commander, medical and health physics people, what should all these people be doing when they're decontaminating a patient or when they're trying to get somebody out of what we're calling the inner cordoned area, basically the place that's the worst, or into the ambulances or whatever. Okay, yeah, and I guess that brings us right to this one. This is kind of the cartoon schematic that we're using. And I've got to be honest, we stole this from the International Atomic Energy Agency. We like to think that we improved it a little bit. They may beg to differ. But we figured that why should we redo what a lot of other really competent people have done before us? So what we're looking at in case, and this would be for a large-scale incident, but you could also see where bits and pieces of this could apply even to a laboratory that's badly contaminated or to an industrial accident. But basically we're figuring there's going to be the inner cordoned area, which is where the highest activity is. If there's a radiological attack or some sort of industrial accident, this is also where the injured people would be, or the contaminated injured people. And then you're going to have some way to get them out into the decontamination area, a place to do the immediate triage, because you don't want somebody to die while you're deconning them. That, well, I guess it would keep your emergency department and your ambulances clean, but it would kind of suck for the person. And then after that, basically just showing all the different areas that we would expect people to be handled, or people or equipment to be staged as you deal with these things. And of course, if there was a really large-scale attack, something like this wouldn't just spring up. It might take several hours to get all these bits and pieces in place. But then hopefully, or hopefully by that time, people will have gone through and understood what it is they're supposed to be doing, and they'll be able to start managing the incident. I guess that's about all for that one. One of the other flowcharts we came up with, flowcharts are fun, except when you're trying to draw them up. But this basically is, we're looking at the on-site radiological and medical triage. And I guess by radiological triage, what I mean, or what this committee means, is trying to figure out who's got enough radiation exposure to hurt them, as opposed to who's got enough just to irritate whoever's in charge of keeping the emergency department deconned. And so if you've got a high exposure to radiation where it has to be included in your clinical decision making,